Here we're going to consider the conservation of energy as well as what exactly is energy. First, let's consider just the word conservation. As used, there are many definitions for conservation. The way we're going to use the word is the last one, the maintenance of a physical quantity during a change. Or to be more specifically, we're going to say when we have a system, which is a collection of physical objects that interact with each other, and the system undergoes some sort of a change of state, or the objects rearrange themselves. They're moving at different velocities, they're in different places. As that happens, there will exist a quantity we could call Q, and that quantity stays the same, which is to say, the value for that quantity before the objects rearrange themselves and the value for the same quantity after the rearrangements will be equal. The initial value of the quantity will equal the final value of the quantity. Then we will say that quantity is conserved. One example of that we're going to see is energy. A system of objects will rearrange themselves, but the amount of energy before they do that will be the same as the amount of energy after they do that. And we'll discover there are other quantities that are conserved. But now we want to ask, okay, if that's what conservation means, what exactly is energy? Well, in one sense, energy is often defined as the ability to do work, but work is defined basically as change in energy. So that often is somewhat redundant. So I have to be a little careful, what exactly do we mean by energy? You kind of know intuitively when you have lots of energy and when you don't. But we're going to define energy basically as the ability of objects to change each other's states, which could be a change in external state, which is to change in motion or acceleration, or an internal change, which could be causing something to heat up or deform. But in one sense, this idea of energy is going to replace Newton's idea of a force. The advantage of Newton's idea of a force is that's a more concrete. You kind of know what a force is. It's a push or a pull. Energy is a little more vague. One person who tried to grapple with what exactly is energy was Richard Feynman, who was a Nobel Prize winning physicist. And one year he was convinced to teach an undergraduate class in introductory physics. And in that class, he described energy using the following analogy. He said, consider Dennis the Menace. Now, if you don't know who Dennis the Menace was, he was basically an earlier version of Bart Simpson. Dennis had a playroom, and in the playroom, there were a bunch of wooden blocks. His mother every day went in and counted the number of blocks and discovered there were always 18 of them. And she believed, therefore, there should always be 18 of them. Until one day she went in and could only count 14 of them. 4 of the blocks appeared to be missing. But she noticed there was this box. The box was locked, but she could measure the mass of the box and noticed the mass of the box had increased by an amount exactly equal to the mass of the 4 missing blocks. So now if she wanted to keep track of the blocks, what she had to do was count the number that she could see and measure the change of mass of this black box. And from that, she could do the following calculation and discover that the number of blocks stayed the same. Until another day, she could only find 6 blocks out, and 8 blocks appeared to be missing. However, when she looked in the bathtub, she noticed the water level in the bathtub had gone up, and it had gone up by a volume equal to the volume of the 8 missing blocks. So now what she had to do to keep track of all the blocks was to measure the mass of this box, the height of the water in the bathtub, and do the calculation of change in mass of the black box divided by the mass of one block, plus the change in height of the water in the tub times the surface area of the tub, subtract the volume of the tub, and divide that by the volume of one of the blocks. That gave you the number of blocks in the tub, plus the number of blocks hidden in the box, plus the numbers you could find on the floor. Add them all up, and you actually got to the number 18. Until one day, all the blocks appeared to be missing. Then she notices in the closet, there's a bag it's hanging from a hook, and the string that's holding it, she notices, has been stretched. And it's been stretched by an amount proportional to the weight of the missing blocks. So now what she can do to find out where all the blocks are is measure the mass of the black box right here, the change in height of the water in the tub, the change in length of this cord, plug them all into this formula to find out how many blocks are in the box, how many blocks are in the tub, and this right here is the weight of the required to stretch the cord divided by the weight of one block. This is the number of blocks that are in this bag right here. Add them all up, and she gets 18. 18 blocks have been accounted for. What Feynman argued is energy is essentially the exact same thing. All the mother notices is that the blocks will go from the box to the tub to the bag, back to the box, and be rearranged, the total number staying the same. Energy is the same thing. Energy can be hidden in different places while the total amount remains constant. And Feynman tried to argue effectively that the meaning of energy is no more significant than the meaning of the number of blocks in Dennis's playroom. And it turns out the conservation of energy actually was uncovered in very much the same way that Dennis's mother discovered that the blocks always stayed constant. And we can consider the different people who contributed to the conservation of energy, starting with Galileo. Galileo was rolling balls down inclined planes, and he noticed no matter what the angle of that plane was, the ball always had the same speed at the bottom. So here he's got a steep incline. If he had a less steep incline, the ball still had the same speed at the bottom. If he then put a second ramp, the ball would roll up that ramp and would roll up to the exact same height it started out at, even if the second incline had a different angle. The way he put it is the ball somehow remembered its initial height. The initial height stayed the same. What he had discovered, without realizing it, was he had a ball that started with a certain amount of potential energy, it got converted into the same amount of kinetic energy, and then was converted back into the same amount of gravitational potential energy, which was just proportional to the height of the ball above the ground. He did not use that terminology to describe what he had uncovered, but that's what we would currently describe it. Another piece to the puzzle came from Christian Huygens, who was basically colliding identical balls on a flat level table. In other words, he was playing billiards. And he noticed the quantity v squared, the velocity of the balls squared, always stayed the same. So here we have a red ball, which is moving and colliding with a stationary blue ball. He measures the velocity of the ball to start out with and squares it. The balls then collide. He measures the velocity of the two balls afterwards, squares this, squares that, adds them together, and he gets the velocity of the initial ball squared. The velocity squared stays the same. What he had uncovered, again, not without really realizing it, was the kinetic energy of the initial ball was then spread among the kinetic energies of the two final balls. The kinetic energy was simply redistributed, but the total amount stayed the same. Another person who contributed to this was Émilie du Châtelet. She was reproducing some experiments done by William Gravesand, who was dropping balls into clay. And what du Châtelet realized that if you increased the height of the ball, so you doubled its velocity when it hit the clay, you would increase the depth that the ball penetrated into the clay by a factor of 4. So when you double the velocity, basically the amount of work it can do, in this case on the clay, quadrupled. Or what she had discovered was the gravitational potential energy of the ball was being converted into kinetic energy, and kinetic energy depended on the square of the velocity. She didn't get much credit for this, in part because I believe she reported her discovery in marginal notes that she made in her translation of Newton's Principia from English into French, rather than in a separate publication. The last person who put this all together and actually formally stated the conservation of energy was James Joule. The experiment he did was he had a container of water, which you'll note is insulated, and this contraption right here has a bunch of paddles that will stir the water, and a pulley right here to which he attached a mass that could fall. And he noticed that if he doubled the mass of the ball that fell, the paddles would turn and would increase the temperature of the water twice as much. If we let the mass fall twice the distance, again, the temperature of the water increased proportionately. And the way he described this was the potential energy of the mass as it fell was being converted into an equivalent amount of thermal energy as the water heated up. Namely, energy was being converted from one form to another while the total stayed the same. He's the first one that described what was happening in exactly those terms, that there was a quantity which was staying the same, it was merely being converted from one type to another. Subsequently, we run across the following, which looks very much like the formula that Dennis the Menace's mother used for keeping track of the blocks. The total energy, which one can calculate if you know the masses, velocities, and positions of objects, equals 1/2 mv squared. We're going to call that the kinetic energy, plus mgh, which we're going to call the gravitational potential energy, plus 1/2 kx squared, which is the energy stored in compressed objects or springs. And this right here is just the formula we use for calculating thermal energy or heat. Add up other forms, which we're not going to consider things like chemical energy, energy stored in bonds. But you add those all up, the total remains the same. That quantity stays the same. The energy may be converted from one form to another, but the total amount of energy will stay the same. Now, the way we're going to finalize this is what we described were a bunch of experiments which kind of hinted at the formulas for calculating the amount of energy stored in different types. The way we're going to calculate an exact formula is using the concept of work. We're going to calculate the work done by an object as it moves from one point to another, and we'll derive the formula for kinetic energy, gravitational potential energy, elastic potential energy, and heat. But the next thing we need to ask ourselves is, have we simply defined a concept whose total remains constant by definition? Namely, every time we find an example where energy isn't conserved, we simply say, well, there has to be a new form of energy, and we then discover what the formula for that is and how we calculate it. We just say, okay, now we have a new form of energy. Is that just circular reasoning? Is energy conserved simply because we have defined it to be conserved? Well, we can change the way we pose the question by instead asking, can we always find a state function, a function that depends on the position and velocities of objects, whose sum always stays constant for closed isolated systems, specifically without making any ad hoc assumptions, so that we only end up with a handful of different types of energy? If the concept of energy conservation requires dozens to hundreds of different types of energy, we'll have to say this is not terribly useful. But if we only end up with a small number of different types of energy, then this will be a useful concept. In addition, the concept of the conservation of energy has made experimentally testable and useful predictions. The first example of that was in radioactive decay. Beta decay originally appeared to violate the conservation of energy. It appeared as though there was less energy coming out than there should be. One proposal for resolving this was, well, maybe when beta decay happens, a radioactive nucleus emits an electron, but it also might emit something else that carries away the missing energy. Because nobody had seen it, this seemed a little suspect, but the proposed particle turned out to be the neutrino. Neutrino is one of the fundamental building blocks of matter in the universe. Its prediction was made based on an apparent violation of the conservation of energy. Neutrinos are hard to detect, so it took many years before neutrinos actually were finally found, and the conservation of energy in beta decay was confirmed, and that the lost energy is indeed carried away by this mysterious neutrino. But a major discovery had been made, and its prediction was based on the conservation of energy. So therefore, we can avoid the circularity because we have repeatedly tested this, and every time we run across an example where energy appears not to be conserved, we always seem to be able to bring the conservation of energy back without having to make a lot of ad hoc assumptions. We've only have a couple of different types of energy, and every time we seem to find that it's violated, we found that in fact it has not. So the conservation of energy does appear to be a perfectly valid scientific concept.